Right now, somewhere in the world, two computers that have never met are about to share a secret. A password, a credit card number, a private message. And they're going to do it over the open internet, a wire that thousands of strangers are quietly listening on. Here's the impossible part. These two machines never agreed on a secret code in advance. They have never spoken before in their lives. So how do they lock a message that only the other one can open, when everyone is watching them do it? The answer isn't a clever trick, it's a piece of mathematics about prime numbers. And once you see how it works, you'll never look at that little padlock in your browser the same way again. Let's start with the part that feels like magic. Imagine I want you to send me a secret, so I do something strange. I buy 1,000 identical padlocks, I leave every one of them hanging open, and I mail them out to anyone who asks. Anybody in the world can take one of my open locks, put their message in a box and snap the lock shut. But here's the thing, once it clicks closed they can't open it again, not even the person who locked it. Because I kept the only key. This is the whole idea behind public key encryption. There are two keys, not one. A public key that locks, which I hand out to everybody. And a private key that unlocks, which never leaves my side. Locking and unlocking are done by different keys. That split, that asymmetry, is what makes the whole thing possible. The only question is, what kind of lock can you build out of pure math? To build a mathematical padlock, we need an operation that is easy to do but practically impossible to undo. And it turns out prime numbers hand us exactly that. Watch. Take two prime numbers, I'll pick small ones, 17 and 23. Multiplying them is effortless. 17 times 23 is 391. A child could do it, a computer does it instantly. Now let me ask you the reverse question. Here's the number 391. Which two primes were multiplied to make it? Suddenly it's not so obvious, is it? You'd have to start testing primes one by one. For this number, that's just annoying. But now imagine I don't use two-digit primes. I use primes with 300 digits each. Multiplying them still takes a computer a fraction of a second. But going backwards, factoring that giant product back into its two primes, would take the fastest computers on Earth longer than the age of the universe. That gap between how easy it is to multiply and how brutally hard it is to factor is the locked door at the heart of RSA. Everything else is just learning how to use that door. Now we need one more idea, and it's a beautiful one. We need to learn how to do math on a clock. Look at a normal clock, it only has the numbers 1 through 12. If it's 10 o'clock and you add 4 hours, you don't get 14 o'clock. You wrap around and get 2. The clock forgets how many times it went past 12. Mathematicians call this modular arithmetic, doing arithmetic where numbers wrap around after hitting some fixed value. We say everything is computed modulo that value. Encryption uses a giant clock, not 12 hours but a clock with millions of positions. And the magic of this wraparound world is this. If you take a number, raise it to a certain power, and let it wrap around the clock, it gets scrambled into something unrecognizable. But there exists a second, special power that, when you apply it, wraps the number all the way back to exactly where it started. One power scrambles, a matching power unscrambles, lock and key. Now we have all the pieces. Let's actually build a working encryption system, start to finish, with real numbers. I'm going to use tiny numbers, so you can follow every single step. Real RSA uses enormous ones, but the recipe is identical. Step 1, pick two prime numbers, I'll choose 5 and 11. Step 2, multiply them to get our clock size. 5 times 11 is 55. We call this number n, and 55 is going to be the number of positions on our clock. Step 3, and this is the secret ingredient, we calculate a hidden number from the two primes. We take each prime, subtract 1 and multiply the results. 5 minus 1 is 4, 11 minus 1 is 10, 4 times 10 is 40. Hold on to that 40. It's the secret that only someone who knows the original primes can easily compute. Step 4, we choose our public locking number, called D. It just needs to share no common factors with 40. 3 works nicely. And now N and E together, 55 and 3, become our public key. We can shout these from the rooftops. Step 5, we find the private unlocking number, called D. D is the special partner of E, the number that, combined with E, undoes the scrambling on our clock. For our numbers, that turns out to be 27. And 27 is the private key. It stays secret forever. Notice how we found it. We needed that hidden 40, and to get 40 easily, you needed to know the primes 5 and 11. No primes, no 40, no 40, no private key. Let's send a secret. Say the message is just the number 7. To encrypt, we take the message, raise it to the power E, that's 3, and wrap it around our clock of 55. 7 cubed is 343. Now we wrap 343 around a clock of 55, and we land on 13. That's it, 13 is the encrypted message, the locked box. We can send the number 13 across the open internet, and to anyone watching, it is meaningless. Now you receive 13, and you have the private key, 27. To decrypt, you do the same kind of step. Take 13, raise it to the power 27, and wrap it around 55. Do that calculation, and out pops the number 7, the original message perfectly recovered. The locked box has opened. One number locked it, a different number opened it, and at no point did the two of us ever share a secret in advance. So why can't an eavesdropper just do the same thing? They saw everything we sent in public. They know the encrypted message 13. They know the public key 55 and 3. To break in, they need the private key 27. And to find 27, they need that hidden number, the 40. But the only easy way to get 40 is to know the two primes that built 55. So the attacker is forced back to the one question we already said is nearly impossible. What are the prime factors of n? For our toy number 55, sure, anyone can see it's 5 times 11. But remember, real systems don't use 55. They use a number with over 600 digits. To crack it, an attacker would have to factor that monster, and that is the door that stays locked for longer than the universe has existed. The security of RSA isn't a promise that it's unbreakable. It's a bet, a very, very good bet, that no one can factor enormous numbers fast enough to matter. And by the way, in the real world, the public locking number is almost always 65,537, a specific prime chosen because it makes the locking step fast while keeping everything safe. Here's where this touches your life. Every time you see that little padlock in your browser, or a web address that starts with HTTPS, a version of this dance just happened. Your computer and the website use public keys to agree on a secret, with strangers watching the whole exchange, and none of them could listen in. The same math lets your laptop check that a software update really came from Apple or Microsoft, and wasn't swapped out by an attacker. That's called a digital signature, and it's basically this idea run in reverse. Banking, messaging, online shopping, the entire trustworthy internet, all of it leans on a quiet fact about prime numbers. That mathematicians were studying for centuries before computers even existed. They had no idea they were building the locks that would one day guard the world. So the next time you type a password and it just works, remember what's underneath it. Not a trick, not a wall. Just two prime numbers multiplied together, guarding a door that's easy to close and almost impossible to force open. If you enjoyed seeing the hidden math behind the things you use every day, you know what to do. Subscribe and I'll see you in the next one.